Hello and welcome to my course. In this series, we will explain hub location problem, one of the most important and significant optimization problem that has a many application in different areas. So hub location problems is quite important and it's wide separated in many different subjects. So we can see that hub location problem can be applied in computer science, and it has some application in telecommunication industry, and we can also see that this problem can be applied in transportation or logistical systems. In addition to that, it has some application in airline industry, so it is quite common for in this industry, and we can also see that it would be successfully applied for some postal companies. So due to the problems related to postal companies, we can see that many researchers and practitioners have tried to use hub location problem in this industry. And I think that it is one of the hot topics in location theory. You may find another theory that would be applied in location theory, but I think that this is one of the most significant and important topics that we can mention here. And also there are different types of hub location problem. We can see here that single hub location problem, PHLP, and also multi-objective PHLP, which has different objective function. It would be seen in many different papers and published in many different journals, and it also different types of this problem, and we can see a wide range of hub location problem that applied in many applications and industry. So I think that it would be better idea to review this paper. This paper actually published in 2013 in Computer and Industrial Engineering. It really gives you general information about hub location problem, literature review papers. So I suggest you to better understand all aspects and of this problem. It's a great idea to read these articles, and I think that there are many different kind of papers you can see in many different journals, but I think that this paper would be quite enough in this regards. So let's move on. Various types of objective function that can be applied in hub location problem. So the first one is minimize impedance and maximize coverage, maximize capacitated coverage, minimize facilities, maximize attendance, and maximize market share. It would be quite common objective function. Another objective function that can be mentioned here is the target market share. So let's take a look at hub location problems. Actually, we have a different customers, and all customers have to be served with the different service centers, and we just assign index I for the customers and index G for service centers. So this red circles just demonstrates the customer that can be distributed in a special area. It can be a city or something like that, and we have also some service centers that be shown as a yellow square, and we have to select a set of these service centers to serve all customers. So our problem is that how many service centers should be selected to minimize all costs of these problems. For any customers, we have a position. It would be geographical position, and we have also demand. It's depend on the customer. It may be products or services. So we have a xci as the x coordinate of customer I, the position of x coordinate, and also we have a yc as a y coordinate of customer I position, and also we have a di denote as a demands for the customer I. For all customers have a different kind of demands, and we have a geographical position for all service centers, xs and ys as a geographical position, and also we have a CAJ as a fixed costs for service centers. For any given pairs between I and J, between any customer and any service center, we have a distance which is shown as dij, and it is quite important. So for our problem we have to determine all distance between any customers and any service centers. So it would be quite critical, and we have to define our measurements. We have a different formula for measuring distance. The most important one is norm P, that can be shown in this formula, and we just define P. We have a different kind of distance. For example, if P would be equal to 1, this is a city block distance, and it would be applied in many application and problem, especially those problems that related to the sea and urban area. It would be a Euclidean distance, and it would be quite common for many mathematics problems. And if P would be equal to infinity, we have a chessboard distance, and in this regard we have many different problems for computer science applications, so it will be used in this area. We have also Minkowski formula. This is a new version of previous formula that we mentioned in previous slides. So just we have a new dimension for this formula. This dimension named degree of Minkowski, which is indicated as a lambda. So in Minkowski formula we have a 3 input x, y, and lambda, and main modification for this formula is that we have a w that can be applied in general formula of measuring distance. So if degree of Minkowski would be equal to 1, we have a city block distance, and we have reached this kind of distance like this. So this is a city block distance, and if lambda would be equal to 2, Euclidean distance would be received. So let's take a look at the city block distance, and suppose that we have a city like this. This is a map of Manhattan, part of the New York. Suppose that we just wanted to measuring distance from this place to this place, so we can no way between this distance from this here, and it doesn't real, so we have to use city block distance like this, and this show the real distance between these two places. The main decision variable that's used in this regard is that we have to determine which service center would be active or open, and which city center would not be active or closed. So we have defined Fj as our decision variable. So if Fj would be equal to 1, it means that service center J would be open, and if Fj would be equal to 0, we have to mention here that service center J is not active or it is closed. So we have a binary problem. So this is our main decision variable. We have to mention here main parameters that can be applied in hub location problems. Suppose that we have different customers and different city centers. So CAJ that is related to the city centers is a fixed cost for opening city center J, and also we have DI determine the demand of customer I. We have also DIJ This is a distance between customer I and service center J. So it would be applied in our objective function. We have also to determine the nearest active service center to the customer I. It would be shown as a dmin I, and this is a general formula for dmin I. It is shown that we have to determine the minimum distance, minimum dij, with respect to that fj would be equal to 1. It means that city center j should be open. And mathematically speaking, we have this formula. It means that dmin I would be minimum of all dij divided to fj. So if fj would be equal to 0, dmin I would be infinitive, so it wouldn't be accepted, it's just rejected. And if fj would be equal to 1, we just determine minimum distance between I and j. So our objective function has two parts, and the first part is related to total distance that can be obtained from this formula. It means that the minimum distance between any of customers and its nearest active service center. So this is just fixed cost for all opening centers. So let's move on solution and representation of these problems. Suppose that we have 9 city centers and we have a different kind of customers. So which of these 9 city centers should be selected to be active and to serve all customers? And since we have a binary problems, the size of our decision variable would be equal to 9 because we have 9 city centers here. This problem, one possible solution would be something like that. This is our chromosome that would be applied in GA, and it actually tells us that this is a different index that used for city centers. For example, it is shown that city center 1 should be closed, so we just deactive this city center, and city center 2 would be active, 3 would be active because, and city center 4 would be closed, and city center 5 also would be closed, and other city center 6 and 7 should be open, and 8 would be closed because it just gets 0. So I think it is enough, and let's just move on Matlab and define our problems.